In this segment, we are looking at the electrolytic cell, whereby electrical energy is used to bring about a non-spontaneous chemical change. In particular, we'll be looking at electrolysis, a process whereby ionic substances are decomposed by passing an electric current through it. So in a sense, the electrolytic cell can be viewed as the reverse of an electrochemical cell. This is what an electrolytic cell would look like. The anode is connected to the positive terminal of the battery. The anode attracts an ion in the electrolyte, and anode is where oxidation occurs. The cathode is the electrode connected to the negative terminal of the battery. The cathode attracts cations in the electrolyte, and reduction occurs at the cathode. One way to help you remember which electrode undergoes oxidation and which one undergoes reduction is this: anox, anode, oxidation. Red cat, cathode, reduction. Let's look at an example, the electrolysis of molten lead-2 bromide. In the electrolyte, there's only the Pb2 plus ion and the Br minus ion. The positive terminal of the battery is connected to the anode. The negative terminal of the battery is connected to the cathode. At the cathode, reduction occurs. Cation Pb2 plus is attracted to it, and Pb2 plus cation will be reduced to solid. At the anode, oxidation occurs. Anions are attracted to the anode, so Br minus anion is oxidized to Br2. In this segment, we will be looking at the selective discharge of ions in an electrolysis reaction. If the electrolysis involves molten ionic compound, whereby the electrolyte contains only one cation and one anion, it is quite straightforward to predict what are the products formed. At the cathode, the cation will be reduced. At the anode, the anion will be oxidized. However, if the electrolysis involves aqueous solution, whereby the electrolyte may contain more than one anion, more than one cation, and there's also water present, the water itself may also be involved in the redox process. Hence, it's not so straightforward to predict what are the products formed. How then do we decide which ion will be discharged at each of the electrodes? There are three factors to consider. We could look at the electrode potentials, the relative concentration of ions, or the nature of electrodes. Electrode potentials are given in the data booklet. At the cathode, reduction occurs, so cations with the most positive E0 value will be discharged first. Now take for example, an aqueous solution that contains both iron 2 plus and copper 2 plus ions. So this would be the E0 value to consider. From the E0 value, the cation with the most positive E0 value will be discharged first, and from the list, copper 2 plus will be the one that will be discharged in preference to iron 2 and water. So the reaction would therefore be the copper 2 plus reduced to copper. At the anode, oxidation occurs. Anions with the most negative E0 value is discharged first. So from the data booklet, you can pick up the relevant half equation and the E0 values. So if we have an aqueous solution containing, say, sulfate and bromide ions, and there's also water present in the aqueous solution, so from the E0 value, the one with the most negative E0 is discharged first. So hence bromide ion will be discharged in preference to water. So the reaction at the anode will be bromide oxidized to bromine. Note that in sulfate, the oxidation number of sulfur is already at its maximum, +6. Hence, it's not possible to further oxidize sulfate. Hence, sulfate will never be discharged at the anode. Let's look at an example. E0 values are given. So the statement here is silver class has a higher tendency to gain electrons compared to H+. And you have to decide if the statement is correct based on the E0 values. Gain electrons, we are referring to a reduction reaction. So reduction reaction, which is a forward reaction in this case. So this cation with the most positive E0 will be the one that's reduced. Hence, this statement is true. The second statement here, magnesium compared to silver. So magnesium, from the E0 value, it would be oxidized. Hence, magnesium has a greater tendency to lose electrons compared to silver. Now pause the video and attempt this question. Resume when you are ready to check your answers. Looking at the two E0 values, the E0 value for fluorine chloride is more positive than the E0 value for fluorine chloride. In other words, fluorine will have a higher tendency to undergo reduction rather than oxidation. Hence, the statement is incorrect. The fluorine is readily reduced, gain electrons compared to fluorine. Part B, looking at the E0 values, chloride has a higher tendency to be oxidized. Hence, it has a higher tendency to lose electrons compared to fluoride. Did you get it right? To recap, factors affecting selective discharge of ions. First factor, electrode potential. At the cathode, cation with the most positive E0 value is discharged first. At the anode, anion with the most negative E0 values will be discharged first. Note that in sulfate, the sulfur is at its highest oxidation state, +6. Hence, it's not possible to further oxidize sulfate. Hence, sulfate would not be oxidized, it would not be discharged in electrolysis. Likewise, the nitrate, the nitrogen is at its highest oxidation state of +5. Hence, nitrate will also not be discharged in the electrolysis. The second factor that we look at is the relative concentration of ions. In general, ions at higher concentration may be discharged in preference to those at lower concentration, even if the reduction potential for the former is not as favorable compared to the latter. Take, for example, the electrolysis of concentrated sodium chloride using graphite electrodes. Graphite is an inert electrode, so it will not participate in a reaction. The species present in the electrolyte will be Na+, Cl-, as well as water. At the cathode, the species present around it will be Na+, cation, and water. At the cathode, reduction occurs. So from the electrode potential, the E0 values, the cation with the more positive E0 will be reduced. Hence, therefore, comparing the two half equations, the tendency is for water to be discharged in preference to Na+. Hence, hydrogen gas will be liberated at the cathode. At the anode, anion Cl- and water are present around it. At the anode, oxidation occurs. So looking at the E0 value, although the E0 for the chlorine chloride is more positive than that for water oxygen, Because of the high concentration of the chloride ion present, equilibrium position shifted such that the oxidation reaction is favored, making the E0 value less positive. Hence, at the anode, chloride will be discharged in preference to water. So the overall observation will be chlorine liberated at the anode and hydrogen gas liberated at the cathode. This table compares the electrolysis of dilute sodium chloride solution versus electrolysis of concentrated sodium chloride solution using graphite cathode and graphite anode. Note that at the cathode, in both cases, hydrogen gas is liberated. However, at the anode, with the concentrated sodium chloride solution, because of the high concentration of chloride ion, chlorine is liberated at the anode instead of oxygen gas. In summary, if the difference between the E0 value is very large, then the ions to be discharged is determined very much by the E0 value. However, if the difference in the E0 value is not that large, a small difference as in this case, then the concentration factor becomes significant when we determine which ion will be discharged at the electrode. So, in the case of concentrated sodium chloride, chlorine gas will be liberated instead of oxygen gas. Another factor that affects the discharge of ions during electrolysis is the nature of electrodes used. In general, the electrode used could be an inert electrode, for example, carbon or platinum. Inert electrodes do not take part in the reactions. The exception is if oxygen gas is liberated at the graphite electrode, then carbon dioxide and carbon monoxide could be formed as byproducts as well. If the anode is inert, it will not undergo oxidation. The inert anode would simply provide a surface area at which the anions would be oxidized. In this case, the anions in the electrolyte are the ones that provide the electrons during the oxidation process. And these electrons will then pass through the anode and exit into the external circuit. The other types of electrodes that could be used in electrolysis are what we call active electrodes. For example, copper, aluminum, zinc. Active electrodes are reactive and so takes part in the electrode reactions. If the anode is active, it will undergo oxidation as well. The metal electrode will dissolve, ions are produced, which goes into the electrolyte, and in the oxidation process, the electron released will then travel to the external circuit. Take for example, the electrolysis of aqueous copper 2 sulfate using platinum electrode. During the process, it is observed that a pink deposit will be formed at the cathode, whereas at the anode, effervescence will be observed. Now, how would we explain this observation? First, we identify the type of electrodes used. In this case, the electrode is platinum, which is inert. Then we identify the species present at each electrode. So at the cathode, the species present will be copper 2 plus ion and water. At the anode, the species present will be the sulfate ion and water. Next, we identify the relevant half equations involved in the reaction of each species at each of the electrodes and determine from the E0 values which reaction would actually take place at each of the electrodes. So in this case, at the cathode, the copper 2+ ion could be reduced, or the water molecule could be reduced. From the data booklet, these are the relevant anode values. For reduction to occur, the one with a more positive anode value will undergo reduction, and so therefore, in this case, the copper 2+ ion will be discharged. So at the cathode, copper 2+ is reduced to copper solid, which will be seen as pink deposit at the cathode. At the anode, water is discharged in preference to the sulfate ion. Recall that the sulfur in the sulfate ion has an oxidation state of +6, which is already at the maximum. Hence, it's not possible for the sulfate ion to be further oxidized. Hence, at the anode, the water would be oxidized to give oxygen gas. Overall observation would therefore be oxygen gas liberated at the anode and copper solid deposited at the cathode. The blue color of the copper sulfate solution slowly fades away as the copper 2+ ions are discharged. Let's look at another example whereby active electrodes are used. The electrolyte is still copper sulfate. This time, the electrode is copper, which is an active electrode. At the anode, we have the sulfate anion and water molecule present. At the cathode, we have the copper 2+ cation and water molecule present. At the anode, oxidation would occur, hence the two half equations to consider would be this. Either the copper anode getting oxidized or the water molecule getting oxidized. Now, from the anode values itself, for oxidation to occur, the one with the more negative or less positive anode value will undergo oxidation. Hence, in this case, at the anode, the copper will be oxidized to copper 2+. The anode, copper anode, therefore dissolves and goes into the solution as Cu2+ ion. At the cathode, reduction occurs. So, the two relevant half equation will be this, is either the copper 2+ cation being reduced or the water molecule being reduced. From the anode values itself, for reduction to occur, the one with a more positive anode value will be discharged. Hence, in this case, the copper 2+ cation would be reduced to give copper. Hence, copper is observed to be deposited at the cathode. Overall observation would therefore be the copper anode dissolves, and at the same time, as copper is deposited at the cathode, the mass of the cathode increases. The intensity of the blue color solution, the copper sulfate solution, remains the same. This is another example using the electrolysis of copper 2 bromide with platinum electrodes. It is observed that during the electrolysis process, pink deposits are observed at the cathode, while the solution around the anode is observed to have turned yellow-orange in color. You are to explain the observations. To do this, first we identify the type of electrodes used. In this case, it is platinum, which is an inert electrode. Next, we identify the species that's present at each of the electrodes. At the cathode, we have the copper 2+ cation and water molecules. At the anode, we have the bromide anion and water molecules present. Next, we identify the relevant half equations involving the reactions of each of the species at each of the electrode and determine from the E0 values which reaction would actually occur at each of the electrode. At the cathode, reduction occur is either the copper 2 plus cation being reduced or the water molecule being reduced. From the E0 value, the one with the more positive E0 value will be the one that is reduced. Hence, in this case, the copper 2 plus cation will be reduced to copper solid. Hence, a pink deposit of copper is seen at the cathode. At the anode, on the other hand, is either the bromide anion being oxidized or water molecule being oxidized. So from the E0 values itself, the one with the more negative or less positive E0 value will be the species that's been oxidized. Hence, in this case, the bromide anion will be oxidized to give bromine. Now, bromine is slightly soluble in water, and hence the solution around the anode will turn orange in color as the bromine form dissolved in it. Let's look at this question. Electrolysis of aqueous sulfuric acid using platinum electrode. You are to state the products formed at the end of the reaction as well as the observations at each of the electrodes. Now pause the video to attempt the question. Resume when you are ready to check your answers. So first, we identify the type of electrode used and the species present in the electrolyte. From the question, the type of electrode used is platinum, which is an inert electrode. The species present from the aqueous sulfuric acid electrolyte would therefore be H plus ion, sulfate anion, and water molecule. At the anode, oxidation occurs. Water will be oxidized because the sulfate anion will not be oxidized since the oxidation number of sulfur in SO42- is +6, which is already at its maximum oxidation state. So sulfate anion will not be further oxidized. Reaction at the anode would therefore be 2 water molecule to give 1 mole of oxygen, 4 H plus ion, and 2 moles of electrons. The products formed at the anode is therefore oxygen gas. At the cathode, the H plus cation could be reduced or the water molecule could be reduced. So from the E0 values given, the one with the more positive E0 value will be the one that undergoes reduction. Hence, in this case, H plus ion will be reduced to hydrogen gas. So at the cathode, hydrogen gas will be liberated. That's the product formed at the cathode. The overall observation would therefore be bubbles of oxygen gas liberated at the anode and bubbles of hydrogen gas liberated at the cathode. Did you get that right? Good. In this segment, we'll look at calculations involved in electrolysis, essentially the application of Faraday's laws of electrolysis. Faraday's first law of electrolysis states that the mass of substance produced at an electrode during electrolysis is proportional to the quantity of electricity passed through it. The quantity of electricity or charge, the symbol capital Q, is given by current times time. The units for current in ampere and time in seconds. So Q equals to I times T. Hence, the mass is proportional to the quantity of electricity, which is Q in coulombs. So we have mass proportional to I times T, I being the current in ampere, T being the time in seconds. Let's look at one example. Here, you are asked to calculate the quantity of electricity if 5 ampere of current is flowed for 6 minutes. So using the formula, Q equals to current times time, current 5 ampere, multiplied by time, which is 6 minutes, we need to convert it to seconds, hence multiplied by 60, so that gives us 1800 coulombs. The quantity of electricity Q has the unit coulombs. Now, what is the quantity of electricity if 3 ampere of current flow for 1 hour? Pause the video, attempt this question, and resume when you're ready to check your answers. Using the formula, charge Q, charge with the quantity of electricity, Q equals to current times time. We have 3 ampere, so I is 3. 1 hour, which is 60 minutes, convert it to seconds. So the time is therefore 60 times 60, and that gives us an answer of 10800 coulombs. Did you get it right? Good. Faraday's second law of electrolysis states that 1 mole of electrons has a charge of 96,500 coulombs. Faraday's constant is given by the symbol F, and it is equivalent to the charge per mole of electrons. Hence, we have 1 mole of electron equivalent to 1 Faraday, which is equivalent to 96,500 coulombs per mole. This is the Faraday's constant F, 96,500 coulombs per mole. The number of Faradays, F, capital F, required to discharge 1 mole of an ion at an electrode during electrolysis is equal to the number of charges on that ion. For example, Na plus 1 electron to give sodium. 1 mole of Na plus reduced to 1 mole of sodium. In the process, 1 mole of electron is taken in. Hence, from the equation, we have 1 Faraday of charge required to liberate 1 mole of sodium. Now, for the discharge of copper-2 cation, 1 mole copper-2 cation requires 2 moles of electron to form 1 mole of copper. Hence, from the equation, we have 2 Faraday of charge required to liberate 1 mole of copper. So in this case, 1 mole of gold, which has a charge of 3 plus, will require 3 mole of electrons to give 1 mole of metallic gold. Hence, from the equation, 3 Faraday equivalent to the charge required to liberate 1 mole of gold. Let's look at an example. Here we have 0.2 Faraday of electricity passed through a solution of copper sulfate. You are to calculate the mass of copper liberated. From the data given, mass of copper liberated from copper sulfate solution, therefore the reaction involves the discharge of copper-2 plus cation to form copper. The half equation would therefore be this: copper-2 plus 2 mole of electron to give copper. From the equation, we have 2 Faraday required to liberate 1 mole of copper. So for the 0.2 Faraday, by proportion, 0.2 Faraday will therefore liberate 0.2 divided by 2 times 1, which is 0.1 mole of copper. Now the question required the mass of copper to be calculated. So using the formula mass equals to number of mole times the AR value can be found from data booklet. We have the mass of copper liberated, which works out to be 6.35 grams. The final answer, leaving it to 3SF with units. Now, pause the video, attempt this question, and resume when you are ready to check your answers. From the question itself, you are asked to calculate the mass of nickel liberated from the electrolysis of nickel sulfate. Hence, the equation here would therefore be nickel 2 plus 2 electron to give nickel. From the equation, 2 Faraday is required to liberate 1 mole of nickel. So for the 2.1 Faraday of electricity that's passed through, the amount of nickel liberated would therefore be 2.1 divided by 2 times the 1, which gives 1.05 mole of nickel. Here you're asked to calculate the mass of nickel. So using the formula, mass equals to number of mole times the AR. AR can be found from the data booklet. That gives us an answer of 61.6 grams. Final answer, leaving to 3SF with the units. Did you get it right? Good. So in summary, the mass of elements liberated during electrolysis depends on 1. The time of passing a steady current, 2. The magnitude of the steady current. In other words, it is the quantity of electricity, which is Faraday's first law. Now, the mass of element liberated also depends on the charge on the ion of the element, which is Faraday's second law. Pause the video and attempt this question. Resume when you're ready to check your answers. Part 1. 27 grams of aluminium, which is equivalent to 27 divided by AR of aluminium, which is 27. That gives us 1 mole. The equation involved will be aluminium 3 plus 3 electrons to give aluminium. So from the equation, 3 Faraday is required to liberate 1 mole of aluminium. We can write it as 1 mole of aluminium equivalent to 3 Faraday. Hence, 3 Faraday will be required in this case to liberate the 27 grams of aluminium. Now part 2, 63.5 grams of copper works out to be 1 mole divided by the AR, mass divided by AR will give you the mole. That works out to be 1 mole. So for the equation, copper 2 plus 2 electron to give copper. So equation itself shows that 1 mole of copper equivalent to 2 Faraday. Hence 2 Faraday will be required to liberate the 63.5 grams of copper. Now 8 grams of oxygen gas is equivalent to mass over the MR, so 8 over 32 or a quarter mole. The equation to liberate oxygen will be this, which you can find from the data booklet. So the equation, we have 4 Faraday required to liberate 1 mole of oxygen gas. Hence, to liberate a quarter mole of oxygen gas, the quantity of electricity required will be 1 Faraday. Do you get it right? Now let's look at another example. To calculate the volume of chlorine gas at STP that will be liberated during the electrolysis by a charge of 1 Faraday. Chlorine gas is liberated from the discharge of chloride ion. The half equation is this: 2 moles of chloride to give 1 mole of chlorine plus 2 moles of electrons. From the equation, 2 Faraday is required to liberate 1 mole of chlorine. So 2 Faraday equivalent to 1 mole of chlorine. For 1 Faraday of charge that's passed through, This is equivalent to half a mole of chlorine. So half a mole of chlorine gas is liberated. The volume at STP will be the number of mole multiplied by the molar gas volume at STP, which is 22.7 dm cube, and that gives us an answer of 11.4 dm cube. Final answer to 3SF with units. Right, pause the video and attempt this question. Resume when you're ready to check your answer. Oxygen gas liberated. The equation, half equation is this, which you can find from the data booklet. So from the equation itself, 4 Faraday is required to liberate 1 mole of oxygen gas, or we can write as 4 Faraday equivalent to 1 mole of oxygen. Now for a charge of 1 Faraday, the amount of oxygen gas liberated would therefore be 1 divided by 4 times the 1 of 0.25 mole of oxygen. Once you know the mole of oxygen, you can work out the volume, mole times the molar gas volume. At RTP, the molar gas volume is 24.0 dm cube, so that gives us an answer of 6.00 dm cube. Final answer 3SF with units. Did you get this right? Good. Now let's look at the next work example. Here you're asked to calculate the mass of lead produced at a cathode by a current of 2 ampere flowing through the molten electro bromide for 30 minutes. This is the electrolyte, molten electro bromide. So the ions present is just a Pb2 plus and the Br minus anion. From the data given, 2 ampere, 30 minutes, that allow us to calculate the charge that has passed through. So charge formula, current times time, current 2 ampere, time 30 minutes, we need to change it to seconds, so multiply by 60. That gives us an answer of 3600 coulombs. Change it to Faraday, divide by the Faraday's constant, and 6,500, that gives us 0.0373 Faraday. Right, lead formed at a cathode comes from the lead 2 plus cation. So lead 2 plus cation pick up 2 more of electron to give lead. The equation itself tells us that 2 Faraday is required to liberate 1 mole of lead. So 2 Faraday equivalent to 1 mole. For a charge of 0.0373 Faraday, the amount of lead liberated will therefore be half of 0.0373, which gives us 0.0187 mole. Now once you know the amount of lead, you can work out the mass. So mass will just be mole, the amount in mole, multiplied by the AR. AR could be found from the data booklet, so that gives us a value of 3.86 grams. Final answer to 3SF with units. Now pause the video, attempt this question, and resume when you're ready to check your answers. From the data given, the current and the time allow us to calculate the charge that's passed through. So using the formula, charge Q equals to current times time, we have 1.5 ampere multiplied by the time, which is 75 minutes. We need to change it to seconds, so multiply it by 60. That gives us 6750 coulomb. Change it to the number of Faraday, divide it by the Faraday's constant, 96,500, and that gives us a value of 0.0699 Faraday. Now we are looking at the mass of aluminium. So aluminium produced at a cathode comes from the discharge of aluminium 3 plus cation. Equation would therefore be this: 1 mole of aluminium 3 plus picking up 3 moles of electron to give a mole of aluminium. So from the equation, 3 Faraday liberates 1 mole of aluminium. Can write as 3 Faraday equivalent to 1 mole of aluminium. So for that amount of charge, 0.0699 Faraday, the amount of aluminium liberated will therefore be 0.0699 divided by 3 times 1, and that gives us a value of 0.0233 mole. Now once we know the amount of aluminium liberated, we can work out the mass, mole times the AR, 27.0, found from the data booklet, and it's also given in the question. That will give us an answer of 0.630 grams. Final answer 3SF with units. Did you get this right? Good. Now let's look at another example. Here you are given the quantity of electricity required to deposit 2.45 grams of silver. The same quantity of electricity also deposit 2.33 grams of an unknown metal M. This M has an oxidation state of +2. The cation is M2+. You are required to calculate the relative atomic mass of M. From the data given, the mole of silver, the amount of silver that's deposited, mass divided by its AR 107.9, can be found from the data booklet. That gives us an answer of 0.0227 mole. The equation to liberate silver is this. 1 mole of silver cation, pick up a mole of electron to give silver. So 1 Faraday equivalent to 1 mole of silver. So for this amount of silver deposited, the quantity of electricity required will therefore be 0.0227 Faraday. Now this amount of electricity is also required to deposit 2.33 grams of the unknown metal M. So from here, the equation will be M2+, picking up 2 more of electrons to give M. The equation itself tells us 2 Faraday is equivalent to 1 mole of M. So for the charge of 0.0227 Faraday, the amount of M liberated would therefore be this, and we get 0.0114 mole. So essentially, the mass of 0.0114 mole of M is this value here, 2.33. To work out the relative atomic mass, which is numerically equal to the mass of 1 mole of M, we just need to work out from here the mass of 1 mole of M, and that numerical value without the units is the relative atomic mass of M. So 204.4. Now try this question, and when you're ready to check your answer, you may resume the video. Very similar to the previous question, we have the quantity of electricity required to deposit 1.85 grams of nickel. It's the same quantity of electricity required to deposit 4.14 grams of unknown metal M. This time M is in the +3 oxidation state. It's the M3+ cation that we're looking at. So from the 1.85 grams of nickel deposited, we can work out the amount, mass divided by the AR of nickel, which is found from the periodic table. So that gives us an answer of 0.0315 mole. Equation, nickel 2+ reduced to nickel, picking up 2 moles of electron. So equation tells us that 2 Faraday is equivalent to 1 mole of nickel. So to deposit 0.0315 mole of nickel, the amount of electricity required will therefore be 0.0315 times 2, which is 0.0630 Faraday. This amount of electricity is also required to deposit 4.14 grams of M. So the equation involved here will be M3 plus 3 more electron to give M. So equation tells us 3 Faraday equivalent to 1 mole. So for this quantity of electricity, 0.0630 Faraday, the amount of M liberated will be this. So mass of 0.0210 mole of M essentially is 4.14 grams given here. So to work out the relative atomic mass, we just need to work out the mass of 1 mole of M. The numerical value will be the relative atomic mass. So mass of 1 mole of M will therefore be 197.1 grams. The numerical value without the units is the relative atomic mass of M. So 197.1. Do you get it right? Good. So to recap, Faraday's law of electrolysis that's used in the calculation, we have the mass of element liberated during electrolysis will depend on 1. The time of passing of the steady current, 2. The magnitude of the steady current. So this is the Faraday's first law, and it also depends on the charge on the ion of the element, which is Faraday's second law. So we have quantity of charge, Q, equals to current times time, current in ampere, time in seconds, and the units of Q is in coulombs. And 1 mole of electrons has a charge of 1 Faraday, which has a value of 96,500 coulombs. In this segment, we will look at the relationship between Faraday constant capital F and Avogadro constant capital L. From Millikan's oil drop experiment, the charge on 1 electron is found to have a value of 1.60 times 10 to the minus 19 coulombs. From Faraday's law, we have 1 Faraday equals to 96,500 coulomb, which is the charge of 1 mole of electrons. Hence, the number of electrons in 1 mole will be equal to the Faraday's constant, 96,500, divided by the charge on 1 electron, 1.60 times 10 to the power minus 19. And that gives us a value of 6.02 times 10 to the power 23, which is Avogadro constant. Hence, we have Avogadro constant, L equals to Faraday F over E, or the relation F equals to LE. Now, let's look at how that relation can be used in calculations involving electrolysis. Here, we have 366 coulomb of charge being passed through to liberate 45.7 cm cube of hydrogen gas, which works out to be 1.90 times 10 to the minus 3 mole by taking the volume of hydrogen gas divided by the molar gas volume at RTP, which is 24 dm cube, change to cm cube becomes 24,000 cm cube. Hence, 1.90 times 10 to the minus 3 mole of hydrogen gas is liberated by 366 coulomb. By proportion, 1 mole of hydrogen gas will therefore be liberated by 366 divided by 1.90 times 10 to the minus 3. That gives us a value of 193,000 coulomb. This is the equation to show how hydrogen gas is liberated when sulfuric acid undergoes hydrolysis. 2 moles of H plus pick up 2 electrons to give hydrogen gas. So from the equation, we have 2 Faraday required to liberate 1 mole of hydrogen gas. From the data given, 1 mole of hydrogen gas liberated by 193,000 coulomb, which means therefore the charge of 2 Faraday is equal to 193,000 coulomb. So the charge of 1 coulomb will therefore be 193,000 divided by 2. That gives us a value of 96,500 coulomb. Now, using the relation F equals to LE, we have L equals to F over E, and that gives us a value of 6.03 times 10 to the power 23. Now pause the video, attempt this question, and resume when you're ready to check your answers. Here in this question, electricity passed through for 5 minutes, current 3 ampere, that will allow us to calculate the charge. 52.9 cm³ of gas liberated. Here we are looking at the electrolysis of dilute sodium chloride solution. Hence the gas that's liberated comes from the discharge of water and is therefore oxygen gas. So from current and time, we have charge Q, which is current times time, current 3 ampere, time 5 minutes, change to second, times 60, that gives us 900 coulombs. Mole of gas liberated, 52.9 cm³ at STP, so divide by the molar gas volume at STP, which is 22.7 dm³, or 22700 cm³, that gives us 2.33 times 10 to the minus 3 mole. So 1 mole of oxygen gas is therefore liberated by 900 divided by this number, which gives us 386,000 coulombs. At the anode, oxidation occurs, water discharge to give oxygen gas. This is the half equation, which you can get from the data booklet. From the equation, 4 Faraday is required to liberate 1 mole of oxygen. And from the data given, 1 mole oxygen liberated by 386,000 coulomb. So the charge on 4 Faraday is therefore equal to 386,000 coulomb. So the charge on 1 Faraday will be 386,000 divided by 4, which gives us a value of 96,500 coulomb. Using the relation F equals LE, L equals to F over E, F is this value here, divided by the charge on 1 electron, and that gives us a value of 6.03 times 10 to the power 23. Did you get this right? Good. Now try this question, and when you're ready to check your answers, you may resume the video. Here, a current of 5 ampere is passed for 16 minutes. The current and time allows us to work out the charge that's passed through using the formula Q equals to I times T, current 0.5 ampere, time 16 minutes, change to second, times 60, that gives us 480 coulombs. 0.16 gram of copper deposited, mass divided by AR of copper, 63.5 found from data booklet, that gives us a value of 2.52 times 10 to the minus 3 moles. So from these two, we have 480 coulombs required to deposit that many mole of copper. So by proportion, to liberate 1 mole of copper, the amount of charge required will be 480 divided by 2.52 times 10 to the minus 3, which gives us a value of 190,500 coulombs. This is the equation to show how copper is deposited. 1 mole of copper 2 plus ion pick up 2 electrons to give 1 mole of copper. From the equation, we have 2 Faraday required to liberate 1 mole of copper. So therefore, the charge on 2 Faraday is equal to this. So we have a proportion. 1 Faraday will be 190,500 coulomb divided by 2. That gives us a value of 95,250 coulombs. Using the relation F equals LE, L equals to F over E, submit the value. F 95250, E charge on an electron, 1.6 times 10 to the minus 19. That gives us a value of 5.95 times 10 to the power 23, Avogadro constant. Did you get this right? Good. In this segment, we'll look at how electrolysis is being applied industrially, in particular in anodizing aluminium and electrolytic purification of copper. Anodizing aluminium is a process of coating aluminium object with a layer of aluminium oxide by means of electrolysis. The setup looks something like this. The aluminum object will be placed as the anode by connecting it to the positive terminal of the battery. The cathode is a graphite cathode which is inert. It is connected to the negative terminal of the battery. The electrolyte is simply sulfuric acid. Hence, the species present in the electrolyte will be H+ ion, the sulfate anion, and water molecule. At the anode, oxidation occurs. Water is discharged because sulfate will never be oxidized since sulfur is already at its maximum oxidation state. Hence, water is oxidized to oxygen gas. The oxygen gas formed will immediately react with the aluminum object to form a layer of aluminum oxide. Hence, the equation at the anode is written as this: 2 aluminum plus 3 water to give aluminum oxide plus 6H plus 6 electrons. At the cathode, reduction occurs. The cation, H+ cation from the sulfuric acid will be reduced to give hydrogen gas. The advantage of anodizing aluminium is that the layer of aluminum oxide will give the object extra protection against corrosion. At the same time, dyes can be easily absorbed onto the anodized layer, hence giving it color as well as protection. Dyed anodized aluminium is very often used in window and door frames and grills. Electrolytic purification of copper. The setup looks like this. The cathode is a thin sheet of pure copper attached to the negative terminal of the battery. The anode is the impure copper attached to the positive terminal of the battery. The impurities in the piece of copper could include things like iron, zinc, silver, gold. Electrolyte is just simply copper sulfate solution. Now at the anode, where the impure copper is, oxidation occurs. So we have copper oxidized to give copper 2 ions. Hence copper from the impure anode will go into the solution as copper 2+ ion. Now impurities in the anode that has E naught value less positive than 0.34 volts will also be oxidized. Hence zinc will dissolve, goes into solution as zinc 2+. Iron impurity will also dissolve, goes into the solution as iron 2+. Impurities with E naught value more positive than 0.34 volts will not be oxidized, it remains in its metallic form. So we have copper, zinc, iron dissolve, going into the solution as ions. Silver and gold doesn't dissolve, remains in the metallic form, and will be collected as anode sludge. So from the anode sludge, precious metal like silver, gold, platinum could be isolated. So the process essentially would be copper from the anode oxidized, going into the solution as copper 2+ ions, and then at the cathode, reduction occur, the copper 2+ ion reduced to copper, and it get deposited onto the cathode. Hence the size of this cathode will get larger and larger as copper is being deposited continuously. Let's compare the electrochemical cell and the electrolytic cell and see in what ways are they different. The electrochemical cell consists of 2 half cells connected by a short bridge. In the external circuit, the electrodes are connected through a high resistance voltmeter which reads the potential difference between the 2 electrodes. The electrolytic cell, on the other hand, consists of 2 electrodes dipping into the same electrolyte. The electrodes are connected to a battery source. The polarity of the electrode depends on the polarity of the terminal to which it is connected to. In the electrochemical cell, the redox reaction is spontaneous. Hence, the chemical energy from the spontaneous redox reaction is converted into electrical energy. In the electrolytic cell, however, the redox reactions are non-spontaneous. An electrical source of energy is needed to drive the non-spontaneous reaction. In both the electrochemical cell and the electrolytic cell, anode is where oxidation occurs, and cathode is where reduction occurs. However, the polarity of the electrodes are quite different. In the electrochemical cell, at the anode, oxidation occurs. The anode in this case is a negative electrode because of the electron that's lost as a result of the oxidation reaction. On the other hand, in the electrolytic cell, the anode is a positive electrode because it is the electrode that's connected to the positive terminal of the battery. Likewise, cathode is where reduction occurs for both the electrochemical cell and electrolytic cell. In the electrochemical cell, the cathode is a positive electrode because electrons are used up in the reduction process. In the electrolytic cell, however, the cathode is a negative electrode because it is the electrode that's connected to the negative terminal of the battery. In the external circuit, electrons will always flow from the anode to the cathode in both the electrochemical cell and the electrolytic cell.